Sajad Sam, this is
Hey,
Token Drop
hey,
week 5, right? Hey, it's a
yep,
month.
yep,
Before we join, I would ask our viewers to maybe just give us some feedback if you can. Leave us a comment or something on what do you think? How can we
yep.
get better? What are you looking, how would you like this thing to go, etc. Any feedback you give us would be really appreciated. We started this just because we had a good time in our own internal meetings talking about these topics, and I thought it would be good to take it and share more broadly. So we'd love to adapt it as per what people would like. So last week we talked about open source and open weight LLMs, and in that we said we talked this week about world models.
hmm
So let's go ahead and do that. And when I first heard the term world models a while ago, I didn't know what the heck it was. And when I read it about it, it seemed to me that it really should be called real world models because it is meant for it's an AI that has been trained on real world data as opposed to an LLM, a large language model, which has been trained on the written word, right? So these LLMs have all been trained on books, magazine articles, web articles, things like that, all written word. And there's a lot of other types of data that LLM, not LLMs, but AI neural networks can get trained on, which is real world physical data, like data, for example, from robotics applications or self-driving car applications or IoT applications or things like that. So maybe the first thing to talk about is what is a world model? Is it a real world model or what is it? And then I got a question about how these things are trained. But maybe we can start off. What do you think, Sajad?
Yeah, in my mind, given, first of all, you know, given that AI, the LLMs of today, they have a good understanding of the world. There's a lot of knowledge. Sorry, I would say, let me backtrack. They got a lot of good knowledge about the world, but do they really have an understanding of how the world works? And that's in doubt right now. Um, and what I think efforts are being made to see how can we infuse uh, world knowledge and world understanding inside these models. And one currently accepted way is to train them on video, for instance, in addition to static knowledge encoded in text. And in a video, you're more likely to see more dynamic events. If you were to hold a ball and let go of it, it's going to fall down and strike the earth. So, and that's a great way to inform viewers about what is gravity. And it's also, there's an implicit understanding here that doing so will also teach the model what is gravity. So that's one way. And given our backgrounds, we've been working on knowledge graphs. I was also toying with this idea. Is a knowledge graph a world model? We're trying to model knowledge as much as we can in a knowledge graph. But no matter how hard you try, you have knowledge as was recorded at some point in time. It is static, it's not dynamic. And I was trying to relate with a knowledge graph with a world model, trying to understand how best can we inform our viewers on, what is a world model if you're rooted in the use of knowledge graphs, or if you understand what knowledge graphs are. So I came up with an idea, and that is world models are nothing but knowledge graphs, which is a static, discrete knowledge, modeled as in as much detail as you can. And one way to build some dynamism in that, which is to really say, how will this knowledge evolve if an event were to occur, right? You have a description of a rubber ball, but unless you push the ball, you're not going to see how well it deforms. And that is a function of not just knowledge representation, but also some amount of reasoning, because the ball is made of rubber. So when you push it, it has that elastic property, which will cause some deformation. And then, and you can actually build probabilistic graphical models with this. So knowledge graphs plus reasoning plus some probabilistic graphical models that inform or predict what might likely happen. I think all three of them combine together to describe what is a world model. And it's a roundabout way of describing what the leading frontier labs are trying to do today. And their belief is that you train a model just like an LLM was trained on text. You train this model with sufficient quantities of maybe video data, and they're going to eventually learn how the world works. So I still think it's a way of infusing a lot of knowledge, but are you deriving understanding out of that is still a moot point.
What do you think, Sam?
I think Sujat struck it on the nail, right? I mean, so basically, when you ask somebody, I mean, there's so much talk about what a world model is. A world model basically is a neural network, right? That learns the dynamics of an environment from data, actually, so that given a current state and an action, it can predict the next state. That's the
Yeah, it's
exact.
not the written, it's not a language model. It's a
So yeah,
information
it is
model.
not. You see, the thing is, the main thing about is the combination of deep learning, large scale data, and modern sequence modeling has made these world models dramatically more capable, right? I mean, because since 2020 and the past year, they have turned into one of the hottest fights in AI right now. Like, I and Sujat were talking about this a few days back, actually. Now, question becomes, why they became suddenly so important, and why is there sudden spotlight, right? The reason I really think is LLMs have impressive mastery over the digital world, but the physical world is still humanity's domain, right? I mean, building an AI that can compose a novel is far easier than developing one that can fold, laundry or navigate a city street or do things like that. Actually, where you can put coffee, etc. These world models are the proposed bridge which they are talking about. The classic illustration of LLM's limits as a language model is that if you train, say, suppose an LLM on simulated New York city taxi trips, they can effectively, give you the directions across Manhattan until it's forced to make a detour, at which point it fails completely. Why? Because the model knows the routes without knowing the city, actually. So the question is, how do you so it is today, it's between it is said to be the bridge between the two worlds, right? I talked
Yeah.
about, yeah, that's all.
But you guys have been talking about video, so I thought that world models also could be used in things like IoT, where you're recording digital data from a physical network of some sort, and then using that to build kind of a digital twin, so to speak, an AI
Indeed.
digital twin.
Yeah. Indeed. I think it's not a discrete, static knowledge that a world model models. It models a continuous space.
Hmm.
So how do you react to events like acceleration is a great example. Motion is a good example. And even sound and signals of any kind or any modality. If it's a continuous wave pattern, then you have a model and if you have a model that understands those continuous wave patterns, then those models then develop the ability to predict what comes next in that signal.
Right. Because
So
there's an
that's,
element of time, it seems like, Sajat. These things you've been talking about.
yeah,
They,
they're
the,
they're temporally connected. Exactly.
yes.
They have the notion of a time, as you rightly said, and they encode the temporal dimension, which graphical static knowledge graph does not model. You can put in a lot of effort to actually index a knowledge graph by time and model time in a knowledge graph, but they're doing a lot of unnatural things to model that. And that also brings us to another question, right? And just going back to what Sam was saying, these are neural networks that learn about a particular, a signal, which is continuous in space. And taking the example of a video, I was thinking, right? I mean, if you train a model, if you held a ball and let go of the ball would drop. And if you do that sufficient number of times and a model is observing that, you're hoping that the model learns gravity.
Mm-hmm.
But one argument I have against that is we don't know what these models are learning. We don't know which of these features they're actually picking up. Is it the fact that it's an object that that's dropping on account of gravity? Is the model learning that? Or is the model learning the color? I held a blue ball and I let go, the blue ball fell down. So blue balls fall down on account of gravity.
Right.
Now, what would happen if I held up a red ball and let go of a red ball? Would that fall down? Right? Would the model have enough sense to realize that the red ball and the blue ball are similar? Or should I train the same model now with the blue ball enough number of times? And should I also do the same with an apple and a pineapple and everything else? So, how many such combinations do I need to train the model with sufficiently enough so that it actually learns gravity well enough? So, I don't know the answer. And because these models are black boxes, we don't know what they're learning. So, it harkens back to the same questions that we had on text, like LLMs, right? How much have they learned? How much do they know? And do you know whether they learned the right concepts or not? Because they're just prediction engines. They're just predicting the right next token. So what happens when they encounter signals that are out of distribution?
Right.
Right? In distribution, we know that they can reliably predict, but out of distribution tokens like red ball versus blue ball or a apple versus a pineapple, would they still learn gravity? Would they still be able to generalize? I don't know.
Mm-hmm. When I was reading about this, one of the things I was interesting to me is it said that these models, these world models, real world models, as I think we should call them, is they're trained on unlabeled data. And I
Yes.
didn't really understand how you can train a world model on unlabeled data. Wouldn't you have to label it to then be able to have it be trained? I don't
Yes, it's
understand.
like most language models, right? Today, if you're trying to train an LLM on text,
Yeah.
so let's say you have a line, Humpty Dumpty sat on a wall. So one clever trick they've come up with on how to train on these language models is, Humpty Dumpty sat on a wall, and then you mask out the last word, wall, and you get the model, you just give the first part of the sentence, Humpty Dumpty sat on a, and then you get the model to make a prediction. The model might predict ball, or the model might predict couch, or whatever. And then the supervision comes in by disclosing to the model, it is not a couch, it was actually the wall. Because
Mm-hmm.
your first sentence was Humpty Dumpty sat on a wall. You actually had that sentence. All you did was you masked out the last word and you try to train the model with all the other words preceding the word wall. And then you try to get the model to predict what the next word would be. And then it could compare itself, or there's a iterative loop that can compare whatever was predicted against whatever was the word. So the human being is not labeling it, right? You're
Hmm.
using this trick to kind of generate supervised labeled training data. So I'd imagine in world models too, you'll play those kinds of tricks,
Right.
which is, let's say you have a frame by frame training. You drop a red ball and you have many frames of recording until it strikes the earth. So you have many frames and you can mask out the last frame where it is actually striking the earth and then ask it to predict. And if it got it wrong, you have supervised training data where you say, hey,
Hmm.
the actual uh,
Yeah.
effect was the final frame was where the ball struck the earth.
Right.
So you actually had the data. So without, you can play those kinds of tricks where you can mask out some parts of your input stream, get the model to predict, and then you disclose what was masked, and the model will realize whether it was right or wrong.
Right.
And that becomes an iterative loop. So you don't really have to do labeling there. So it looks like unsupervised training, but you're actually supervising with this clever trick.
Right.
Yeah.
When we worked in one of our previous companies, we talked about digital twins. Remember the whole digital twin business? And it
Yeah.
was very valuable, but it was very difficult to create those digital twins, especially for some of these very complex manufacturing systems. Very valuable, but very complex. It seems to me that these world models are an AI version of those old digital twins.
Yes, indeed. So the IoT team that we used to work with,
Yeah,
they were used to building physics models, right?
yeah,
They spent the better part of their careers building physics
yeah,
models. So when they're modeling how fluids flow within a factory through a pipe, they would apply knowledge of physics and hydraulics,
yeah,
and they'd come up with these equations
yeah.
that kind of model those
It was
flows.
programs. They had to write these
Yeah.
programs.
So they would do that, and it was incredibly hard until neural networks came along. And as Sam said, you can actually use the neural network to train in narrow enough domains. And then you need some safeguards and controls to make sure that you're using them for making predictions within the distribution space that they were trained on. Because if they go beyond the distribution space, then they could make
Correct.
incorrect predictions.
Yeah. Sam,
And
you look like you want to say something.
yeah,
No, no, actually, Sujat is right, and I think he was alluding to a lot of stuff, which is exactly what I was trying to say. So basically, digital twin comes from engineering, right? Originally, NASA used early versions for the Apollo, right? The term took off in manufacturing and is now everywhere, from BMW factories to digital twin of the patient in healthcare, etc. Right? I mean, so this is not something new. It's been in the ecosystem for quite some time. A twin is tied to a specific physical instance. This
Right.
turbine in this plant, right? I mean, and fed live by its sensors. I mean, it usually combines a CAD or physical model, right, with a data stream, like
Right.
and the physics model is a structural part, and the data stream is the live state. You can use it to monitor health, right? For example, that run what ifs, right? And what if I increase the load 15% and schedule maintenance? The twin is grounded in one real thing, in a way, right? I mean, and it is a very important way of really getting to know the ecosystem, right? I mean, a modern thing increasingly has a learned dynamics component in it, actually, on top of the physics model, right? Because pure physics simulation is slow and brittle. That's what Sajad is saying. And a neural surrogate trained on the twins' history can predict faster and handle phenomena the physics model didn't capture, actually. That is where the digital twin plus world model becomes very relevant. Conversely, a world model trained inside a high fidelity twin is how you get cheap synthetic training data, actually, for robots without crashing real ones, actually. So the question is, previously synthetic data people used to simulate using GANs actually. They now do deliver that kind of data for robots using the digital twin plus world model actually.
So did I understand you correctly? You're saying that you would use these world models inside of a digital twin. Is that what you're
Yeah,
saying?
they can be. So the digital twin is the live dashboard with the
Yeah.
physics under it, and the world model is the intuition. That's it. That's how you classify it, actually.
So, and we've been able to do that even with simpler technologies like, um, we were able to model supply chains.
Hmm.
We're able to model supply chains with the knowledge graph. So you have static knowledge of the supply chain. And then on that, you could do some cause cause effect modeling. What happens if one of the suppliers were down, or the link or the logistics between one supplier and another supplier were to be disrupted? What would happen to the flow of materials through the whole supply chain? So we could do that. And then we started building more sophisticated models. We started building Bayesian models on top of this to model risk. And actually, we applied that in the case of um, I think we did this for one of the leading automotive companies in Europe. And we also did that for one of the leading phone companies out here in the US to model supply chains and to model uncertainty in the supply chain using some Bayesian network models and to see how risks propagate to this. And to some degree, I would say that's a digital twin of the supply chain, the real world supply chain. And you could also argue that that's also a model of the world of the
Hmm.
domain called supply chain for that
Correct.
particular company. So knowledge graphs in their most evolved sense, which combine when you combine them with reasoning and you combine them with this uncertainty, you combine them with causality, you combine them with this probabilistic reasoning capabilities, then you're actually approximating a world model with those capabilities. But then, and you have the ability to uniquely control how the world would react, or how the model should react to different events, and and that will allow you to simulate failure scenarios. It would allow you to simulate what if conditions. You could, in fact, one of our customers went out and in my past life went out and used this concept to model manufacturing in a semiconductor fabrication process. It's a complex process. I mean, many step, multi-step complex semiconductor process, and all of that was modeled. Each step was modeled as a node in a knowledge graph. And now you have these complex nodes and you have this complex network and the flow of materials over this network and the processing that occurs. With that, they were able to at least get a sense of what's going on it was like a digital twin of their
Hmm.
manufacturing process. And they were able to report on what stage a given unit of wafer was in, and what would happen if something were to get disrupted, and how to reroute its processing if there are alternatives. So those are the kind of what if scenarios they were trying to model and report on.
I think what you're saying is that the knowledge graph was tremendous value back then, but what you do have today is you have a world model that you can add to the knowledge graph, combine them, and
Yes, you could,
and
yeah,
get
you could enhance knowledge graphs with some of these
yeah.
probabilistic graphical reasoning, probabilistic graphical models, and emulate what these world models that are being spoken about today,
Hmm.
right? Some of the leading labs like Jan LeCun, he left Meta.
Right.
They joined a company called AMI, I think, and they're trying to build world models. And then there's another company, Fei Li. She was a professor at Stanford, and she is building a world model lab. And what they're, I think, if my understanding serves me right, they're trying to train models from video. And the idea is that models so trained with the video content would be you can then embody those models inside robotic,
Hmm.
constructs. So then it becomes easier to then build robots that can walk into an unknown kitchen and maybe prepare an omelet for you.
Hmm.
So that's the holy grail. That's the route they've taken. And one can argue against that as well, which is how much training data do you need? And is that adequate and sufficient? Or can you do that a little bit more deterministically, but in narrow enough domains? So it's a classical conundrum, right? In our text world, LLMs versus the graphs that we use,
Yeah.
exactly the same analogies can be drawn even in this context as well.
So is it fair to say, Sajat, that the knowledge graph gives you the construct of the real world and the world model brings in the temporal aspects that's missing in the knowledge graph? Is that a good way to look at it?
What I'm saying is knowledge graphs extended with additional capabilities
Hmm.
can approximate the world models that you're speaking about in narrow enough domains, right? In a given domain. I spoke about supply chain, we spoke
Hmm.
about manufacturing processes. So you could do that even with graphs and with some additional capabilities, but the domains are limited, quite narrow. So as long as you constrain the application to those domains, then you're building a world model for that given domain. Like you're building a world model for the supply chain domain, or you're
Right,
building a world model for semiconductor manufacturing.
right.
That's if that's the world you live in, then you can model that world through this method, which is a lot more deterministic, controllable, and transparent, or the classical neural network method, which is, I mean, they learn fast, quite rapidly, and you get to train these models with less effort, much less, significantly lesser effort. Of course, it costs you more time, it costs you more money and more resources. And so you have, and maybe you might be able to combine the two. So
Sure.
these graphical or knowledge graph based models can serve as guardrails to these neural
Absolutely.
network based world models.
Yeah, the
So you could,
grounding.
yeah, you could do that exactly the way we're doing today in
Yeah.
Thicker. So we use neural networks, but we also use graphs, and we combine the two in the best way possible to construct,
Mhm.
trustworthy systems. You could actually do that even in the context of today's definition of real world
Right.
models and graphs.
Okay, I think we've reached our time here. Sam, anything else you want to add, or Sajat, anything you want
No,
to
nothing like because I concur with what Sujad was saying, right? I mean,
add?
grounding the world model in knowledge graph entities, which you talked about, right? I mean, the second is the twin state as the bridge, right? I mean, this is the cleanest story for integration right now, which means that the twins uh, um, state vector serves as both the KG's runtime instantiation and the world model's input, actually, right? And closing the loop is the fact when the world model predicts a failure, that prediction should become a temporary node or edge in the knowledge graph, actually. So trigger reasoning and update on the twins risk state. And most systems today do parts of the full loop, right, in production. So when you get all of them working together, you get that holistic loop actually, and that is where we are headed, right? I mean,
Mhm.
so I think this is really a current area of research actually in particular, and there is a lot of things that are going on, especially with respect to the KG, how it is represented, how the digital twin works as a dashboard, and the world model, right, helps in doing
Right.
and putting that together. Yeah, yeah.
Well, thanks, guys, for the discussion. A good discussion about world models or I'm going to call them real world models.
Yeah.
So anyway,
Yeah, thank
thanks,
you.
and we'll talk to you guys later.
Thank you, guys. Thank you. Bye-bye.